like I said, this will be quick, I think, and not too difficult, but I just want to talk about it conceptually. And we talked about this, again, with the gas law, or the gas tube demo that I did where the hydrochloric acid and the ammonia gas were racing and the ammonia won. So we talked about that yesterday. You don't have to write down this formula. You do not need to know this for your test, okay? But I'll show it to you just so you can notice something here. Notice how the V1 and the V2, the M1 and the M2 are on opposite sides of the equation there, okay? There's probably an easier way, there's an easier equation, I think, that relates these to one another. And you don't have to know this one either, okay? But, any of you seen that equation before? Kinetic energy? I didn't know if you guys did that in 8th grade or not. So this is the formula for kinetic energy. M stands for mass, V stands for velocity. Basically what this says is if you're playing football, you want a small guy traveling at slow speeds to hit you because he will have less energy, right? You don't want a big guy at a fast speed coming at you or it's going to really hurt. That's a lot of energy. Does that make sense? Okay? This is mass, this is velocity. So here's the thing. If I give a particle a certain amount of kinetic energy, based on this formula, it can move faster if its mass is low, okay? So I'm giving something a certain amount of energy, and remember, this is the big dog, little dog thing that we talked about yesterday. You give the big dog and the little dog the exact same amount of energy. The little dog can do more as far as its speed. It can move faster than the big dog because there's not as much mass to move, right? So you give a small particle a certain amount of energy, and it can zip all over the place, okay? But you give a big particle that same amount of energy, and it's going to move quite a bit slower because there's more mass there to move around. Does that make sense? Okay. All right, some of you are with me, I can tell. All right. Again, this part you don't necessarily have to worry about, okay? The rate of diffusion is inversely proportional to the square root of the gas's molar mass, okay? But what I do want you to know is the bigger the molecule, the more massive the molecule, the slower it's going to move, okay? And the smaller it is, the faster it's going to move, all right? So that's this part right here. Particles of low molar mass travel faster, I should say faster, than heavier particles, okay? And, then the opposite would obviously be true, right? Particles of high molar mass travel slower, okay? Now, this is assuming that they're at the same temperature and pressure, okay? So if you have two gases, same temperature, same pressure, the small one moves faster, okay? And that's what happened in our demo back there. The ammonia gas is smaller. They were both at the same temperature and pressure. The ammonia moved faster than the hydrochloric acid because it was lighter. It had less mass, okay? Does that make sense? I feel like you guys were understanding it yesterday, so this is just the same basic thing. We're just putting it on notes instead. Okay, so the practice problems here ask you to do calculations, but I'm not going to ask you to do calculations. I'm going to ask you to just do this conceptually, all right? So oxygen molecules have an average speed of about 480 meters per second at room temperature. By the way, let's take a second to think about that. See, I don't have a good comparison here because I don't know how many meters a second a car travels. How many cars? See, I'd have to do a conversion from, what, is it 30-ish? Okay. All right, so we'll go with like 30 meters per second if you're going 70 miles an hour, okay? This gas particle is going 480 meters per second, okay? That's really fast, all right? So gas particles, they move quickly, right? That should be the point there. Now some of you, well, you're probably not even asking this question, but I'm going to answer a question you weren't asking anyway. Let's say that I have a spray bottle of cologne or perfume, and I spray it on this side of the room. It takes you a little while to smell it on that side of the room, doesn't it? Well, if these things are traveling at 480 meters per second, why can you not smell it instantly? Well, it does disperse, but why doesn't it, 480 meters per second, that's like it's there. It does, but if it's going 480 meters per second, this room is nowhere near 480 meters long. Okay, so in 1 second, you should be able to smell this, right? So why is it not making it to you that quickly? Well, no, I mean, there aren't that many molecules, that's true, but it shouldn't take that many of them for you to be able to smell it. Here's what's going on. You guys walked through the, well, okay, I know you have walked through the freshman hallway recently, like on the way through this class, right? I really don't like that hallway, okay? Because the freshmen, no offense, I mean, you guys, I know you were freshmen last year, but don't throw it. But now you're sophomores, right? So you know better. But those freshmen, they do not understand. They're supposed to get out of the way. They're not supposed to stand in the middle of the hallway, right? Yeah, or yeah, you've got the two hallways coming together, and then there's this huge traffic jam of people, and we need a traffic signal there, I think. Anyway, point is, that's kind of like the gas molecules, right? I mean, it takes forever to just walk through there because you have to go in and out between all of these other people that are there, okay? There are a lot of gas molecules in this room. So the perfume starts over here, it gets going, and then it hits something, and that slows it down, right? It knocks it in a different direction, and it hits something again. It keeps hitting things, and it's got to kind of work its way through all the rest of the gas that's in this room before it can get to you. So if you let a gas particle go in a vacuum where there's no other gas particles, it will shoot across the room at 480 meters per second. But in this room, it's not traveling nearly that fast because it's crowded, right? There's other gas molecules that it has to work its way through before it can get to you. So it keeps hitting stuff, stopping, starting, until it eventually gets to you. Does that make sense? It's moving through the freshman hallway, okay? It's basically what's happening in this room. So in case you were interested. All right, so that's kind of an aside there. But oxygen molecules are traveling this fast, and at the same temperature, we want to know what's the speed of sulfur hexafluoride. But we're not actually going to calculate the speed because that would require us to use this formula, which we're not going to do. I just want you to tell me, is the sulfur hexafluoride going to be traveling faster or slower than the oxygen at that temperature? Faster. How would we know? Well, you could put in the formula, or you could just, I would prefer for you to just think about it, right? So you don't have to use this formula.
Find the weight of the oxygen molecules versus the sulfur hexafluoride.
Okay. So we would need to find the molar mass of the oxygen versus the molar mass of the SF6. That'll tell us which one is bigger, right? If it's bigger, it moves slower. Yep. So, I mean, you can probably tell just by looking at it, SF6 is going to be quite a bit bigger. Can you tell that? Yeah, now, technically, you don't know this yet, but oxygen in the air typically exists as O2. All right, so it'd be about 32, okay? But that's still nowhere close to, yeah, that's S by itself, basically, okay? So then you add the 6 fluorines in there. This is much bigger, right? Which means it moves slower, okay? So the SF6 would move slower than the O2. And that's all. If you have a question like this on the test, that's all it's going to be. Okay? Out of these two gases, which one moves faster? And then all you have to do is calculate the molar masses. That's pretty easy, right? You guys can do that? Okay. All right, so one more little practice problem here. Oh, well, it's basically the same thing, except a little bit simpler. This one, do you have this one on your? Yeah, you do. Okay. At the same temperature, which molecule travels faster, oxygen or nitrogen? Okay, now which one will, okay, so it's asking which one will travel faster. Yeah, this one's close because they're right next to each other, right? But the nitrogen's smaller, just by a little bit, okay? The nitrogen is, again, in the air, these are going to be N2 and O2, but for our purposes, it doesn't matter. 14.007 for the nitrogen and 15.999 for the oxygen, okay? So the nitrogen is going to move a little bit faster. Just a little bit, though. Now, it says how much faster. You'd have to use the equation to calculate that, so I'm not going to ask you that question. All right? That's all you need to do with Graham's law. No, there's just one S there, and then 6 F. Yeah, if it's don't worry about the diatomic thing yet. That's what that's called. It's diatomic, two atoms. We will talk about that. Actually, maybe it's in the next unit. Okay, but you don't need to know that yet. Okay. All right, so that's it for that. Now, the last thing I need to show you is letter G. There's nothing to fill in on letter G, but we haven't talked about it yet. Okay, so let's go to that quickly. Yeah, Avogadro, except Avogadro did some other stuff. Actually, he didn't come up with his number. You guys remember that from the video? He had died, and then they named the number in honor of him. Okay, so Avogadro's law, this one he actually came up with. Any gas at STP, now we know what STP is because we talked about it the other day, right? Standard temperature and pressure, will occupy 22.4 liters per 1 mole, okay? Now, this is just giving you another conversion to work with. It's basically saying 1 mole of gas is equal to 22.4 liters. You don't have to remember this. I will give this to you on the test. And you may or may not even need to use it, honestly. But I'll give it to you just in case. Okay? But basically, this is just saying any gas at standard temperature and pressure, which means if it's at 1 atmosphere pressure and 273 Kelvin, any gas will have a volume of 22.4 liters. 1 mole of that gas will have a volume of 22.4 liters. That's how much space it will take up. Doesn't matter what gas it is. Could be helium, could be hydrogen, could be oxygen, could be nitrogen, whatever gas it is, they're all the same, okay? And if you have 1 mole of any gas at STP, but you knew this one, right? You'll have 1 mole of anything is 6.02 times 10 to the 23rd particles. Whoops, you're right. Sorry, 6.02 is what that's supposed to say, not 6.20. Switch those two around. Is it that way on the, no, it's right on the, it's right on your notes. So I guess you don't have to switch that around. And technically, we've just learned 6.02. That number keeps going for a long time, so you can cross out that extra 2 at the end if it makes you uncomfortable. But it's, I mean, that's just going 1 digit further than we normally go with the number, which is actually what I accidentally did here on the R that I gave you today. The R you'll get on the test is 0.0821. Yeah, I rounded it in a different place than it was on the notes, and I didn't realize that until after. Okay? All right, so that's pretty much it. I will say for the test, which we're going to review for the test tomorrow, we'll take it on Thursday. But for the test, you're going to need to know standard temperature and pressure. Okay, and again, we'll work on that a little bit tomorrow, but you'll need to know standard temperature is 0 Celsius, standard pressure is 1 atmosphere, but those are pretty easy numbers to remember, right? Like I said, this I will give you, okay, and we'll talk about everything else you need to know for the test tomorrow when we review for it, okay? All right, that's it.